Get started. So we were talking about electric field last time, and we were working on a problem from worksheet 6. We were working on number 2. So on number 2, there are 3 charges on the 3 corners of a square. So let's consider a square. So that's the square, and there are 3 charges. One on this corner, which is Q3, and that's 4 microcoulomb. No, sorry, that's the number 1. So that's plus 8 microcoulomb. There's one on this corner, which is Q1 minus 4 microcoulomb, and one on this corner, which is Q2 is minus 5 microcoulomb, and each side is 30 centimeters. So we want to find the net electric field on this corner. Okay. So how do we find the net electric field? So we first need to find the electric field due to individual charges. Okay. And when we find electric field, you need to imagine that there is a test charge at that point. Okay, so we want to find electric field at this point. So imagine that there is a small positive charge at that point. Okay, you don't need to write it, but just imagine that there is a small positive charge. That means if there is a small positive charge there, then this charge Q1 will attract this positive charge, because this is negative, so it will attract the positive charge. So the electric field, again, electric field is force of this charge, source charge, this is called source charge, on this test charge, okay, this small charge. So the force would be along this direction. So let's call it E1, force per unit charge, okay, force per unit charge, force felt by this charge. And force of this charge on this test charge, or a small charge, would also be pointing towards the source charge, so it would be up, so call that E2. And then force due to this third one would be away from this charge, because it tends to repel, because this is positive and this is also positive, so it tends to repel the test charge. So let's draw the force, the direction of electric field away from the charge. So it would be away like that. Okay, so we have all 3 electric fields, and then we need to add the electric fields vectorically to get the net electric field. So what that means is we first need to find individual ones, so E1. So the formula for electric field is K times charge times distance squared. Okay. So K is 9 times 10 to 9 Newton meters squared per coulomb squared. Charge is this charge. Okay, it's a magnitude, so we don't need to consider the negative sign. So 4 times micro is 10 to minus 6 10 to negative 6 coulombs, and then distance is this distance, which is 30 centimeters. So 30, convert that to meters, 10 to negative 2 and square. So that gives me 4 times 10 to 5 Newton per coulomb. So that's 4, that will give me 4 times 10 to 5 Newton per coulomb. And this would also be same because you have same distance. No, that would be same because this charge is different. Okay, although the distance is same, but the charge is different, so you need to find that also. So Q2 will generate electric field E2. So K, we are dealing with second charge, and then distance of that charge from that point is, let's call that d2 squared. So 9 times 10 to 9. Okay, I want to write the unit. Charge Q2 is 5 times 10 to 6 negative 6 coulombs over distance is 30 centimeters, converting that to meters squared. That will give me 5 times 10 to 5 Newton per coulomb. Okay, and then I also need to find the electric field due to the third charge, which is K Q3 over d3 squared. Again, 9 times 10 to 9. Charge is 8 microcoulomb, which is 10 to negative 6 coulomb. And the distance, now we need to find this distance. What's that distance? We know this distance. Okay, this is 3 or 30 centimeters, and we know this distance. Using the Pythagoras theorem, we can find the distance. So 30 squared plus 30 squared and square root of that. That will, what's that? I don't have a number here. So that's 30 times square root of 2. So 1.4 times 3. 1.4 times 3 to 4.2. Is that 42 centimeters? Something? Huh? Yeah, 42.4. Okay, 42.4. So 42.4 times 10 to minus 2 meters squared. Do that calculation, you get I have a different number here. So what, can you guys do the calculation? Seems like this one has wrong number. Does anyone have a number for this? 4 times 10 to 5, okay, 4 times 10 to 5 Newton per coulomb. So we got all 3 electric fields. So let's redraw the vectors, because we want to now add these 3 vectors. So we need to redraw our vectors. So this is the coordinate. Okay. Oops. So we have this x axis and this y axis. So we have 3 vectors here. One is this way, the next one is this way, and the other one is this way. So we have E1, E2 and E3. So we separate the x and y components of these vectors, because we want to add separately x component and separately y components. That's how we add the vectors, if you remember from your physics 1. So put all the x components of electric field on this side and all the y components of electric field on this side. So E1, it's all along x direction, so we don't need to worry about its y component. E1 is all along x direction, but the left side is considered as negative and right is considered positive, so this is negative. Okay. E2 is all along y direction, so, and it's positive because it's all along the positive y. Now we need to resolve this into 2 components, okay, x component and y component. So E3 has both x and y components. For that we need to know this angle to resolve it. So what's that angle? Let's go back to the diagram up here. Okay, so we want this angle, okay, which is also equal to this angle, because they are vertically opposite angles. So if we could find this angle, then that would be that angle also. So we can use this triangle to find that angle. Okay, so you can use either sine, cosine, tan, anything, okay, because we know all the sides. So let's say tan theta. Tan theta is opposite, which is 30 centimeters over this adjacent, which is also 30 centimeters. Then theta would be tan inverse of minus 1, tan inverse of 1, so that's 1. So that is that 45 degrees? Yeah. So that's 45 degrees. Okay, so you get this angle to be 45 degrees. That means this angle is also 45 degrees. So what's the x component of E3? This thing is the x component, and x component is E3 cosine 45 degrees. Okay. Y component would be, this is y component, which is E3 sine 45 degrees. Hopefully you already dealt with this in your physics 1 multiple times to find x and y components. So x component is E3 cosine 45 degrees, and again, because it's along positive x, so it's positive, and y component is along negative y, so we need to put minus sign here. E3 sine 45 degrees. Okay. and then you add all the x and y components. So our sum of all the x components would be minus E1 plus E3 cosine 45 degrees, and our sum of all the y components would be E2 minus E3 sine 45 degrees. So let's plug in the values. E1, what we got for E1? E1 is 4 times 10 to 5 Newton per Coulomb, plus E3 what did we get for E3? 4, same number. So 4 times 10 to 5 Newton per Coulomb, and we have cosine 45 degrees. Okay. Here E2, what we got for E2? 5 times 10 to 5. So that's 5 times 10 to 5 Newton per Coulomb, minus E3 is 4 times 10 to 5 Newton per Coulomb, and then that's sine 45 degrees. So sum of all the x components of electric field is, if you do the calculation, you get minus 1.17 times 10 to 5 Newton per Coulomb, and sum of all the y components of electric field 2.17 times 10 to 5 Newton per Coulomb. So those are the x and y components. So to get the net, do you guys remember what you do to get the net electric field? Yes. What happened? Oh no, what happened? Okay. So yes, you use Pythagoras theorem to get the net. So E net would be, take square root of Ex squared plus Ey squared. Okay, that gives you the net field. So Ex is minus 1.17 times 10 to 5 squared, plus Ey is 2.17 times 10 to 5 Newton per Coulomb squared. Okay, if you do the math, you get 2.47 times 10 to 5 Newton per Coulomb. And we know that electric field is a vector quantity, so just by finding the magnitude does not completely answer the question. So we also need to find the direction. To find the direction, we need to find the angle. An angle is given by, you guys did this in physics 1 also. So whenever you have 2 vectors or 3 vectors, you are adding those vectors, and then eventually you find angle for the net force or net something. So that's given by tan inverse of y component over over x component. So tan inverse y component is 2.17 times 10 to 5, and then x component is negative 1.17 times 10 to 5, and if you do that calculation, you get 118 degrees. So that's the direction with respect to positive x-axis. Okay, so this is with respect to positive x-axis. There is another way to express the vector. So this is one way. So you can use any way you like. So another way is you can express the electric field vector as x component, which is minus 1.17 times 10 to 5 Newton per Coulomb. So this is along x direction. So this is I hat. I hat means it's along x direction, plus 2.17 times 10 to 5 Newton per Coulomb. This is along y direction, so j hat. Okay. So you can use either this representation or this representation. Either one is fine. Now, there's another question on the same problem. Find the force on a 3 microcoulomb charge if it is placed at the fourth corner. So if you place this is the electric field due to the 3 charges at this point. We know the net electric field at this point. Okay. So we know that there is some electric field at that point, and if we bring a charge and place the charge at that point, the charge will feel some force. So if I place a charge here, which is positive charge that has the value of 3 microcoulomb, so this will feel some force. So what's that force? Okay, so the force would be, we know that from the definition of electric field is force felt by some charge q naught, or it could be some other charge also. Let's just say q. Okay, and if we want to find the force, then the force would be, rearranging this equation, we can write q times E. So q, in this case q is 3 microcoulombs, 10 to minus 6 coulombs, and the electric field at that point is that. Okay, or you can also use this one, whichever you want. So for the magnitude you can just use 2.47 times 10 to 5 Newton Coulomb and do the calculation. That will give you, this is negative, so 1.48 Newton. Okay, and again we also need direction. Direction of the force and the direction of electric field is always same. Okay, the force is always along the direction of electric field, so same direction, so at 118 degrees. Okay, so let me ask you guys a question. Let's look at this question. So what's the direction of the net force on the charge on the top? So we want to find the direction of force due to these two charges. So we have this charge, and we want to find the force, the direction of the force at this point. Is the direction along A, or is the direction along B, C, or D? So think about that. Oops, sorry. No, not that one. Sorry, that one. So what's the answer? So this one will try to push this charge away from it because they are both positive. So they will push. So this one will push it that way. Okay. And this one, because this is negative and that's positive, it will try to pull it towards it. So that way. So we have these two vectors. So this is force due to this positive charge, and this is the force due to this negative charge, and the net would be the sum of these two vectors. Okay, vectorical sum. If you have two vectors, this vector and that vector, which way would be the sum? It cannot be up, it cannot be to the left, it cannot be down, it must be in between, right? So that's the net vector. So the net force on this one would be that. Okay. So now let's think about this one. Same kind of question. So instead of force, now you have electric field, but it's same idea. You have two charges, this one and this one. What would be the net field due to these two charges at this point? No idea? Whenever you are thinking about field, imagine that there is a positive charge. Okay, so you have a charge here. Imagine that you're finding force on a small positive charge. So field means force applied by this charge on this small tiny charge. So which way would be the force? That way, right? We have a negative charge here. Which way would be the force on this positive, tiny positive charge due to that negative? To the left, because it's attracting, right? So there would be force to the left. Now we have this one to the right and one to the left, but which one would be longer? Which one would be greater? Left would be greater because it's closer, right? So there would be more force for closer charges than for the farther charges. So less, because electric field depends on the distance. It's k q over r or d squared. So it depends on distance. Closer the distance, bigger is the electric field. So this one is electric field is greater. So if you subtract this from that, this one is greater. If you subtract this from that, then the net would be along left. So that means that's the right answer, because left is greater, so you will get the resultant on the left. Okay. So that's the electric field. So everything we do in this chapter is basically application of the things you learned in Physics 1. So let me ask you guys a couple of concepts that you learned in Physics 1, and just to see if you guys remember. So we learned about physics in Physics 1. We learned about force. Do you guys remember force? You know force, right? Force is basically given from Newton's second law. Net force is given by mass times acceleration, right? Right? If you apply same amount of force on both sides, okay, let's say 10 Newton and 10 Newton, then there won't be any acceleration. Acceleration would be 0. This is called equilibrium, static equilibrium. So in static equilibrium, if net sum of all the forces would be 0. Okay. But if you apply unequal force, let's say a bigger force on this side, 20 Newton, and a smaller force on this side, 10 Newton, then you will have acceleration in this case. Okay, acceleration is non-zero. let's talk about another concept here. Work. You learn work, the concept of work. What is work? Do you guys remember what is work? Yeah, so work is the force you apply on an object which produces some distance or displacement, okay, Fd. If it doesn't produce any displacement, you are not doing any work. So no matter how hard I push the wall is not moving, so there's no work. So if the force produces a displacement, then you do the work. If there is no displacement, there's no work. And there is another thing called energy. And we have two types of energy we learned in physics 1. One is potential energy. Do you guys remember what potential energy is? Object at rest. Potential energy is, yeah, it's possessed by object at rest, but that's not complete. It also needs to have some height. Okay, it's due to the configuration. Okay, if I raise this at some height, now this one has potential energy. So potential energy is energy due to the configuration of an object. For example, if I have a spring, okay, if I stress the spring, now I change the configuration. That means this one has potential energy. Or if I compress the spring, I change the configuration. So this one has potential energy. In equilibrium, in normal condition, it doesn't have any energy, no potential energy. But I need to change the configuration to have the potential energy in the object. Or I can raise that object to some height that will produce the potential energy. And kinetic energy, what is kinetic energy? Yeah, kinetic energy is energy possessed by any moving object. Okay, energy possessed by moving object. Next thing is work energy theorem. Do you guys learn work energy theorem in physics 1? THEOREM. What that is if I do some work on an object, let's say if I do work on this chair, the work has to go somewhere, right? So if I push it, the work has to go somewhere. Where does the work go? What happens to the work I did on that object? Yes. It's converted to, or it's used to change the kinetic energy of the object. So the work I did on the object is used to change the kinetic energy. It has some kinetic energy in the beginning, and then because of the work, its kinetic energy is changed. Okay, so final kinetic energy minus initial kinetic energy. Okay. And the next thing is conservation of mechanical energy. So we'll be using all these ideas in this chapter. Conservation of mechanical energy. Mechanical means potential and kinetic energy. It says that energy is conserved, right? So if you drop an object from some height, so at the highest point it has all potential energy, it's not moving, and at lowest point, just before hitting the ground, it will have all kinetic energy. In between, it will have combination of potential and kinetic. Potential and kinetic. So there will be more potential on the top, less kinetic on the upper part, but there will be more kinetic on the bottom part and less potential energy on this part. Okay, but the total would be always equal. Okay, total energy is sum of potential and kinetic energy. That would always remain constant. So that's the conservation of energy. So sum of potential and kinetic energy always remains constant. Okay, so let's see all these concepts in this context now. So we just saw the force, okay, and we saw the relationship between force and electric field. Electric field does not depend on charge. Okay, it's the intrinsic property of the source charge. It doesn't depend on the other charge. It basically tells us, if I were to put a small test positive charge at some point, how much force it can exert on that. Okay, so electric field defines the intrinsic property of this source charge. It's the ability of this charge to apply force on this source charge. Whether you put the force or not, that doesn't matter. It just tells us how much force it can exert on that. Okay, so electric field is force on that charge. If it is a small test charge, we use the letter Q naught. Q naught means it's 1 coulomb, okay, unit charge. If I want to find force given the electric field, then I use Q times E. Okay. Now we have another concept here. We have a source charge, and I have some other charge. Okay, let's say this is Q1 and this is Q2, and this is initially at some infinitely far distance, and I push this charge towards it. Now because these both are positive charges, so in order to move this charge closer to this, I need to do some work, otherwise this is trying to push it away. So I need to do some work to bring it closer to this positive charge. Okay, so I put some work. Okay, and then when I'm holding this charge at this point, or even here, I'm holding the charge here, the work I did to bring the charge from here to here, this charge is converted to potential energy. Okay, so far away from this charge, there is no potential energy because it's far away, so there's no potential energy. But I changed the configuration of this charge. I moved it from here to here. Okay, so there is change in configuration, and when I change the configuration, the energy I get by changing the configuration is what we call potential energy. Okay, so in this case, so the energy possessed by this charge due to the change in configuration is called electric potential energy. It's the same kind of energy that we talked in gravitational field or gravitational force, but here it's potential energy due to the charge. Okay, so this one has now potential energy, and depending on the distance, the charges may have different potential energies. So the potential energy here at this point would be greater than the potential energy here. The potential energy here would be greater than the potential energy here. Okay, so the electric potential energy is denoted by U. It is given by K times charge, this source charge Q1, and the charge that we are bringing from the infinity, let's say it Q2, and the distance. Okay, distance is d between the source charge and let's just write it d. So that's the distance between the source charge and the charge that we are bringing from infinity. So its unit is joules, same as the unit of energy. Now there is another term which we often use in physics more than this electric potential energy, is called electric potential. So electric potential is, let's say I have a source charge. If I were to bring a small test charge from infinitely far distance to some distance closer to this charge, how much potential energy this can have? Okay, so potential energy of a source of a point charge. Point charge means it's a unit charge, 1 coulomb charge. Potential energy of a point charge due to the source charge. So that's electric potential, which is denoted by V. So this is potential energy, is energy of any charge, any amount of charge, but electric potential is energy of a unit charge. Okay, so energy per unit charge. You can also say unit charge or test charge. It's also called test charge. So U, we know from this formula, U is K times source charge. This is the second charge. In this case, we are considering the test charge. Test charge is denoted by Q naught. Okay, Q naught, and then distance between the two charges. That's on the top for U, and from on the bottom we have this Q naught. Okay, this whole over Q naught, and this Q naught and Q naught cancel, so we would be left with K Q1 over D. Okay, so this is again energy of a unit charge due to some source charge. Now in this formula there is only one kind of charge here, which is the source charge, so we don't even need to write 1 here. We can just write K Q over D. Okay, so let's look at number 3. So how do we deal with how to calculate electric potential? So we have 3 charges, 2 nanocoulomb, another one is 4 nanocoulomb, and the next one is 6 nanocoulomb. All are positive. So that's 7 centimeters. That's 7 centimeters. And we want to find electric potential due to these 3 charges at this point. Okay, meaning what that means is we want to know if I were to bring a test charge here, a small test charge here, what would be the potential energy of that test charge due to these 3 charges. Okay, it's obvious whenever we talk about potential, it's obvious that we are talking about energy of a test charge, so we don't even need to write this charge here. Okay, it's just obvious whenever you find potential. If you find potential energy, then you need to put the charge here, because potential energy depends on the amount of charge, because potential energy is k q1 q2 over d. Okay, so it depends on how much charge you are putting here, potential energy. But if you are finding just the potential, it's the energy due to the unit charge, okay, 1 coulomb charge. It's obvious, so we don't need to show the charge. Okay, so we want to find potential at that point due to these 3 charges. So just like the electric field calculation, we just find the individual potentials. But one very important thing here is electric potential is a scalar quantity, so we don't need to deal with the vector. Electric potential is a scalar. Okay, so no need to do vector addition. Just add as you add a scalar number. Vector addition. Okay, so find potential due to this one first. Okay, let's call this 1, call this 2, call this 3. So find V1 potential at that point due to 1, which is k q1 source charge times distance. Okay, so 9 times 10 to 9 Newton meter squared per coulomb squared. Charge is 2 times 10 to nano is negative 9 coulomb. Distance, this distance is 8 centimeters. So 8 times 10 to minus 2 meter. There is no square. And one very important thing here is, because we are dealing with a scalar, we are not dealing with vector, so we don't have a magnitude here, unlike in the electric field. In electric field, we take care of the sign when we do the vector addition, so we need to put the magnitude here for electric field. But for electric potential, do not put the magnitude. Okay, if it is a negative, put minus sign there. Okay, that's the difference. Very important thing. So that's V1. V2 is k q2d. Let's call this d1, d2. So k is 9 times 10 to 9 Newton meters squared per coulomb squared. The second charge is 4 nanocoulomb, which is 4 times 10 to negative 9 coulomb. Distance between 2 and this point, that would be square root of 8 squared plus 7 squared. Okay, so 8 squared plus 7 squared, that's the distance, and that's in centimeters, so I need to do 10 to negative 2 meter. And then V3 is k q3 d3. K is 9 times 10 to 9. I will not write the unit. Q3 is 6 times 10 to negative 9 coulomb. And then distance. So that's that distance, which is 8 squared plus this whole distance is 14 squared. Oh, by the way, I didn't put the square root here, so I need to put square root here. Okay, so square root of 8 squared plus 14 squared, and that's in centimeters. I need to convert that to meters. 10 to negative 2 meter. Okay, so tell me the numbers if you guys have the numbers. I don't have answers with me. And again, addition is straightforward. So V total would be just adding the 3 V's. Okay, V1 plus V2 plus V3. And that gives you the potential. Potential is, because we know potential is energy per unit charge, energy is joules and charge is coulomb, so joule per coulomb. Okay. Okay, we are out of time. Please complete this and then we'll look at some other problems next time. Joule per coulomb. It's also called volts. We will use the volts unit later, but for now let's just use joules per coulomb.